Pick up a warm cup. The heat moves into your hand. Something passed between the cup and your skin. You felt it happen. Now try to find it. Not the warmth your skin registered, the thing that moved. Point to it. Describe its shape. Tell me where it was sitting inside the ceramic before it reached you. You cannot. And that is not a failure of attention. That is the first sign that what just happened is not what it looked like. We grow up inside a word, energy, that behaves like a noun. It fills batteries. It flows through wires. Bodies burn it. Engines convert it. Stars release it. The grammar of the word implies a substance, something that sits inside objects and waits, something with a location, something you can run out of. But no instrument has ever isolated it. No experiment has ever extracted it from matter and held it separately. When physicists calculate it, they are not measuring a thing. They are computing a number that describes a state, a number that, under certain conditions, does not change. What that number actually is, what it is tracking, and why the universe bothers to keep it constant at all, that is what this is about. Does the physical law underneath something as ordinary as a warm cup lead somewhere genuinely strange? And if energy was never a substance to begin with, what exactly have we been conserving all this time? If you enjoy exploring questions like these, make sure to like this video and consider subscribing to the channel. It helps others find their way here. Now, with that said, let's return to the situation at hand. The cup is still warm. Something happened when you held it, and the explanation for what that something actually is runs deeper than the word we gave it. Take a spring and compress it. Press both ends toward each other until the coil tightens and resists. Now hold it there. Something in you wants to say the spring is storing energy, that you pushed energy into it the way you push air into a balloon. But watch what actually happened. The metal did not absorb anything. No substance entered it. The atoms in the coil shifted positions relative to each other. The distances between them changed. The forces between them changed as a consequence. That is the entire event, a rearrangement, a new geometric relationship between parts that were already there. Now, release it. The coil snaps outward. Something drives that motion, and whatever drove it was already present in the compressed state, waiting, not as a fluid inside the metal, not as a charge stored in the material, as a configuration, as the particular way the parts were arranged relative to each other and the forces that arrangement produced. This is what storage actually is. Every time physics uses that word, it is describing a configuration of matter that has the capacity to change another configuration. A raised weight is not full of energy the way a jar is full of water. It is in a particular relationship with the gravitational field around it, a relationship that, if allowed to change, will produce motion somewhere else. The height is not a container. It is a description of where the object sits inside a force structure, and that position carries consequences. Chemical energy follows the same logic. A molecule of glucose does not have energy packed inside it like cargo. It has a particular arrangement of atoms, specific bonds at specific angles holding specific charges in specific proximity. When that arrangement is broken and reformed into different molecules, the new configuration sits lower in the landscape of possible states. The difference between where the system started and where it ended is what physics calls the energy released. It was never a stored substance. It was a gap between two arrangements. This distinction matters more than it first appears, because if storage is always a configuration, then the question of where energy is located starts to dissolve. You cannot point to the place inside the spring where the energy lives, because the energy is not in any one place. It is a property of the relationship between parts. Remove one part and the relationship changes. Remove the gravitational field and the raised weight has nowhere to fall. The configuration only carries consequences inside a context. Energy does not sit in objects. It describes what objects in relation to each other are capable of doing next. That last word is important. Next. Energy is always forward-facing. It is not a record of what happened. It is a structural description of what a system can do from where it currently sits. The compressed spring, the raised weight, the glucose molecule. Each one occupies a position in a landscape of possible states. Energy is the measure of how much further they can fall through that landscape, not what they contain, what they can still become, which means the moment anything changes, the spring releases, the weight drops, the molecule breaks. What physics tracks is not the movement of a substance from one object to another. It tracks the shift between configurations. Something that was arranged one way is now arranged another way, and the number that describes the capacity of the system has redistributed across the new arrangement. Nothing moved in the way a liquid moves. The accounting changed. Watch a billiard ball cross a table and strike a second ball that was sitting still. The first ball stops. The second ball moves. Something passed between them. You can see the effect clearly enough. The moving ball had it. The still ball received it. And now the roles have reversed. It looks exactly like a handoff. A substance leaving one object and entering another. But stay inside the collision for a moment. At the instant of contact, the surface of the first ball presses against the surface of the second. The atoms at the boundary compress slightly. Forces propagate through the material. The first ball decelerates because the second ball is pushing back against it. Newton's third law, two forces, same interaction. The second ball accelerates because the first ball is pushing into it. There is no packet of energy that detaches from one and attaches to the other. There is a contact force acting across a boundary, changing the velocity of both objects simultaneously. What changes is the motion of each ball. What physics then computes after the fact is a number describing each ball's new state. The number that described the first ball's capacity went down. The number describing the second ball's capacity went up. The sum stayed the same. That sum staying the same is what gets called conservation. But notice what was actually conserved. A number, a calculated quantity derived from the masses and velocities of the objects involved. The conservation is a statement about the accounting, not about the movement of a substance. Nothing flowed. Two configurations changed simultaneously through a shared interaction, and the number that describes the total system remained constant across that change. Heat works the same way, though the interaction is harder to see. When the warm cup meets your cooler hand, what is actually happening is a difference in the average motion of atoms on each side of the boundary. The atoms in the ceramic are vibrating faster. The atoms in your skin are vibrating slower. At the contact surface, faster-moving atoms collide with slower-moving atoms. The faster ones slow down slightly. The slower ones speed up slightly. This repeats across billions of collisions per second, gradually evening out the difference in average motion across the boundary. What you feel as warmth arriving in your hand is your skin's atoms being jostled into faster motion by the ceramic's atoms. No thermal fluid crossed from one material to the other. The word heat describes the direction of that statistical evening out process, not a substance in transit. This was actually a hard-won clarification in physics. For a long time, heat was treated as a fluid called caloric. a weightless substance that flowed from hot objects into cold ones. The model was coherent enough to make predictions. It was also entirely wrong. There is no caloric. There never was. What there is a difference in the kinetic states of atoms on either side of a boundary, and a statistical tendency for that difference to reduce over time through contact interactions. The transfer is not a flow of stuff. It is a coordinated shift in the motion of particles that were already there. And this pattern holds across every form of what we call energy transfer. Electrical current through a wire is not energy flowing like water through a pipe. It is a wave of changing electromagnetic field propagating through the wire, nudging electrons forward in a coordinated drift, doing work on the circuit as it goes. Light carrying energy across space is not a substance moving through a vacuum. It is an oscillating field whose configuration changes as it propagates, and whose interaction with matter changes the configuration of whatever it meets. In every case, what physics is describing is a change in how things are arranged and how fast they are moving, and a number that tracks the total capacity of the system across all those changes. That number never belongs to the interaction itself. It belongs to the states on either side of it, before and after. Here is what the system could do before the interaction. Here is what it can do now. The interaction is the mechanism, the number is the ledger, and the ledger, so far, always balances. Take everything established so far and press on it from a different angle. Energy describes configurations. It tracks the capacity of a system to change. It is not a substance that moves between objects. Fine. But even if you accept all of that, a reasonable question remains. The configuration has to live somewhere. The spring is a real object in a real location. The raised weight is at a specific height above a specific floor. The vibrating atoms are inside a specific piece of ceramic. So even if energy is a property of these arrangements rather than a substance inside them, surely it has a location. Surely you can point to the region of space where the energy is. This is where the picture gets genuinely harder to hold. Consider the gravitational potential energy of a ball sitting on a shelf. The number that describes its capacity to fall and do work depends on its height above the floor. But the floor is an arbitrary choice. Move the reference point to the basement and the number changes. Move it to sea level and it changes again. The ball has not moved. Its relationship to the earth has not changed. Only the coordinate you chose to measure from has shifted, and the energy value shifted with it. A substance cannot behave this way. A fixed quantity of water in a jar does not change when you relabel the floor, but energy does, which means the number is not describing something intrinsic to the ball or to the space around it. It is describing a relationship between the ball and a reference, and relationships do not have addresses. Go deeper. In electromagnetic theory, energy can be described as residing in the field itself, spread through the space around charged objects and current-carrying wires, distributed across a volume rather than concentrated at a point. That sounds like a location, but the field exists everywhere the interaction reaches, which in the case of gravity and electromagnetism means it falls off with distance but never fully disappears. The boundary of the field is not a clean line, and when two fields overlap, as they always do in any real physical situation, the energy of the combined field is not simply the sum of the energies of the individual fields. The interaction between them contributes a term that belongs to neither field alone. You cannot carve the total up and assign each piece a home. In general relativity, the problem deepens further. Gravity is no longer a force field sitting in flat space. It is the curvature of space-time itself, and there is no way to define the energy density of gravitational curvature at a specific point in a manner that holds across all coordinate systems. Different observers, moving differently through the same space-time, will calculate different values for the gravitational energy in a given region. None of them is wrong. The quantity is not invariant at the local level. It does not have a fixed location because it does not have a fixed value, independent of who is measuring and from where. What this means is that the question, where is the energy, does not have a clean answer even in principle. For simple systems in flat space-time, you can often write down an energy density and integrate it over a volume and get a useful number. But that number depends on the coordinate system, it depends on the reference frame, it depends on what you decide to include in your accounting. The number is real in the sense that it is consistent and predictive. It is not real in the sense of marking out a region of space that contains a fixed amount of something. Physicists are not troubled by this the way non-physicists sometimes expect them to be, because the power of energy as a concept was never that it pointed to a location. It was that the number stayed constant. You could track it across wildly different physical processes, mechanical, thermal, electrical, chemical, and the total never drifted. That consistency is what made it useful, and that consistency turns out to have nothing to do with energy being a substance with an address. It has to do with something much more fundamental about the structure of physical law itself, something that took until the early 20th century to name properly. But before that naming becomes clear, there is a prior question worth sitting with. If energy has no fixed location, and its value depends on the reference frame, and it is not a substance that moves, then what exactly is the number tracking? What is it that stays constant when the configuration of a system changes? What is being conserved, if not a stuff? There is a line from Richard Feynman that physicists return to often. He was describing energy to a general audience, and he said something that sounds almost deflationary at first. He said there is a numerical quantity that does not change when things happen. That is it. That is the whole concept. A number that stays the same across change. No mechanism, no substance, no image of what it looks like. Just a number, and the fact that it holds. That description can feel like a disappointment until you sit with what it actually implies. A number that is conserved across every physical process ever tested, across collisions, combustions, electrical discharges, nuclear reactions, gravitational collapses, is not a trivial thing. It is one of the most non-obvious facts about reality that physics has ever uncovered. The universe did not have to work this way. There was no logical necessity sitting outside of physics that demanded a conserved quantity exist at all. And yet every time anyone has looked, across every scale and every interaction, the number holds. But what is the number actually assigned to? This is the step that tends to get skipped in most descriptions of energy, and skipping it is where the substance illusion sneaks back in. Energy is not a property of an object in isolation. It is a property of a state, and a state is not just the object, it is the object plus its context, its velocity relative to a reference frame, its position within a force field, its internal configuration of bonds and charges and temperatures. Change any part of the context and the number changes, even if the object itself is untouched. A rock sitting on a ledge has a gravitational potential energy that depends on the height of the ledge, the strength of the local gravitational field, and the reference point you chose to measure from. None of those are properties of the rock alone. They are relational. They describe where the rock sits inside a larger physical situation. The kinetic energy of the same rock falling is a function of its velocity, which only has meaning relative to something else. Even the internal thermal energy of the rock, the kinetic energy of its vibrating atoms, is defined relative to the average motion of those atoms around their equilibrium positions. Strip away every relational context, and the number has nothing to attach to. This is what physicists mean, in practice, when they work with energy. They are not measuring a thing inside the system, they are characterizing the system's state, the full description of how all its parts are arranged and moving, and extracting a number from that characterization. The number is a functional. It takes the entire state as its input and returns a single scalar value as its output. That value is the energy, and the reason it is useful is not that it tells you what the system contains. It is that it tells you what the system can do from where it currently sits, and it lets you check whether the accounting is consistent before and after anything happens. This is also why energy has no units that point to a substance. A joule is a kilogram times a meter squared divided by a second squared. It is a unit of mechanical action, force applied over distance, or equivalently, mass times velocity squared. It has the dimensions of a dynamic relationship, not the dimensions of a stuff. You would not describe a quantity of water in kilograms times meters squared per second squared, but you would describe the capacity of a moving object to exert force over a distance in exactly those terms. The units themselves are telling you that energy is a description of interaction potential, not a measure of content, and yet the number holds. Across every transformation, every interaction, every rearrangement of matter and field and motion, when you add up all the values assigned to all the states in a closed system, the total does not change. Something is being preserved. The question that has been building through every segment so far now has enough ground under it to be asked properly. Why? Why does this number assigned to states, defined relationally, carrying no fixed location, remain constant across all the change the universe produces? What is the universe actually doing when it conserves energy? A stretched bow holds an arrow against it. The archer has not released yet. Nothing is moving, and yet something about that system is different from the same bow and arrow sitting relaxed on a table. The difference is not visible in any single component. The bow looks like a bow, the arrow looks like an arrow, but the relationship between them, the tension in the limbs, the angle of the string, the force each part is exerting on every other part, describes a system that is capable of producing a specific outcome. Point it, release it, and the arrow crosses the field. That capacity is real, it is measurable, and it belongs entirely to the current state of the system, not to any substance inside it. This is what the number is tracking. Every time physics assigns an energy value to a state, it is quantifying that state's capacity to change something else. A moving object can exert a force over a distance. That capacity is its kinetic energy. A compressed spring can push against whatever contacts it. That capacity is its elastic potential energy. A hot gas can expand and drive a piston. That capacity is its internal thermal energy. In every case, the number answers the same question. Given where this system currently sits, how much change can it produce in the world around it? That framing makes conservation feel less like a bookkeeping rule and more like a structural constraint. If energy is the measure of a system's capacity to produce change, then conservation says that capacity does not appear from nowhere and does not vanish into nothing. Every change produced by a system reduces its own capacity by exactly the amount transferred to whatever it acted upon. The archer's bow loses exactly the capacity that the arrow gains. The cooling cup loses exactly the capacity that the warming hand receives. The number moves between states, but the total across the full system stays fixed. What makes this non-trivial is that the capacity takes so many different forms: motion, position, temperature, chemical bonding, electromagnetic fields, nuclear configuration. These look nothing like each other at the surface, and yet physics finds a way to assign a number to each of them using the same unit, and to show that the sum of all those numbers across a closed system remains constant regardless of how the forms convert into one another. Kinetic becomes thermal, thermal becomes chemical, chemical becomes electromagnetic. The form changes completely. The total does not. That is not obvious. It did not have to be true. The fact that such wildly different physical phenomena can be placed on a single common ledger, and that the ledger always balances, is pointing at something deep about the structure of the laws governing all of them. Something they share, something underneath the surface differences that ties them together into a single conserved quantity. Finding that something requires stepping back from the phenomena themselves and asking a question about the laws instead of about the things the laws describe. The ledger balances, every time, across every process, across every scale at which physics has been tested. That consistency is so reliable that it functions as a diagnostic tool. When an experiment appears to violate it, physicists do not conclude that conservation broke down. They go looking for what was missed. When radioactive decay seemed to produce electrons carrying less energy than the reaction should have released, the assumption was not that energy had disappeared. It was that something else was carrying the remainder away undetected, that something turned out to be the neutrino, a particle whose existence was inferred entirely from the energy gap, years before anyone detected it directly. The conservation law was trusted enough to use as evidence for the existence of an undiscovered particle. That is not the behavior of a rough approximation. That is the behavior of a structural feature of physical law. But reliability is not the same as explanation. The ledger balances. That much is clear. What is not yet clear is why it has to. A law that holds in every tested case could still be a deep contingent fact about this particular universe, rather than a necessity built into the fabric of physical law itself. To ask why energy is conserved is to ask whether there is something about the structure of reality that makes conservation unavoidable. Something that would make a universe without it not merely unusual, but physically incoherent. That question has a precise answer, but reaching it requires a shift in what you are looking at. Every segment so far has focused on physical systems: springs, cups, arrows, atoms, fields. The question now has to turn toward the laws themselves, not what the laws govern, but what properties the laws possess. Because it turns out that conservation is not a fact about matter. It is a fact about the laws that matter obeys. And the relevant property of those laws is not something most people think to look for. Consider what it would mean for a physical law to change over time. Gravity pulling objects together with a certain strength on a Tuesday, and a slightly different strength on a Wednesday. The electromagnetic force behaving differently in the afternoon than it did in the morning. These scenarios are not just unfamiliar. They would make physics as a discipline impossible. Prediction would fail not because our models were incomplete, but because the rules themselves were shifting underneath every calculation. The entire enterprise of science rests on a background assumption so pervasive it rarely gets named. The assumption that the laws of physics are the same now as they were a moment ago. That an experiment run today gives the same result as the same experiment run yesterday. that the rules do not drift. That assumption has a name in the language of physics. It is called time translation symmetry, and it is not merely a philosophical comfort or a methodological convenience. It is a precise mathematical property of the equations that govern physical systems. And once you see what that property implies, once you follow the logic of what it means for a law to be invariant under shifts in time, the conservation of energy stops looking like a fact that needs to be checked experimentally. It starts looking like something that could not have been otherwise. In 1915, a mathematician named Noether proved something that changed the foundations of physics without most people outside of physics ever hearing about it. The result was not a new law of nature. It was a demonstration of where laws of nature come from. Specifically, it showed that every continuous symmetry in the laws governing a physical system produces a conserved quantity in that system, not as a coincidence, not as a pattern observed across many cases, as a mathematical certainty following necessarily from the structure of the equations themselves. The word symmetry here means something precise. A symmetry is a transformation you can apply to a system that leaves the governing equations unchanged. Rotate the system in space. If the equations look the same after the rotation, then rotational symmetry holds. Shift the system to a different location. If the equations are unaffected, then spatial translation symmetry holds. Each of these symmetries, Noether showed, corresponds to exactly one conserved quantity. Rotational symmetry produces conservation of angular momentum. Spatial translation symmetry produces conservation of linear momentum. And time translation symmetry, the invariance of physical law under shifts in time, produces conservation of energy. This is the answer to why the ledger balances. Energy is conserved not because matter has some intrinsic tendency to preserve a substance, and not because physicists decided it was a useful accounting rule. It is conserved because the laws of physics do not change from one moment to the next. Those two facts are not merely correlated. They are the same fact, expressed in two different languages. The consistency of physical law across time and the conservation of energy are mathematically equivalent statements. You cannot have one without the other. That equivalence is worth pausing on. It means that every time you have confirmed energy conservation in any experiment, every collision measured, every chemical reaction tracked, every electrical circuit balanced, you were simultaneously confirming that the laws of physics had not changed between the start and end of the measurement. And every time a clock ticks forward without the laws of physics shifting, energy is being conserved somewhere as a direct consequence. The two are locked together at the level of mathematical structure, not merely associated by observation. It also means that the question of why energy is conserved dissolves into a deeper question. Why are the laws of physics the same across time? And here the answer becomes harder to give, because this symmetry is not derived from anything more fundamental within current physics. It is a foundational feature of the structure of known physical law. The equations that govern mechanics, electromagnetism, and quantum theory are all time translation invariant in flat space-time. That invariance is where the conservation comes from. Asking why the laws are time-symmetric is asking why the laws are what they are. A question physics can describe with great precision, but cannot answer from something deeper, at least not yet. What Noether's theorem does is remove the mystery from conservation itself. The ledger does not balance because energy is a persistent substance that cannot be created or destroyed. It balances because the rules of the game are not changing while the game is being played, and that reframing from substance to symmetry is not a small adjustment to the picture. It replaces the picture entirely. Take the same experiment and run it twice. Same equipment, same initial conditions, same procedure, but separated by an interval of time. A week apart, a year apart, a century apart. If the results match, something has been confirmed that goes deeper than the experiment itself. The laws governing the outcome did not change between the two runs. The rules that determined what happened the first time were still in place the second time. That stability is not guaranteed by anything visible in the experimental setup. It is a property of the laws themselves, and it holds, as far as every measurement ever taken can determine, without exception. This is time translation symmetry stated plainly, not as an abstract mathematical property, but as a physical fact with direct consequences. The equations that describe how a system evolves from one moment to the next do not contain time as an explicit variable. They describe relationships between quantities, position, velocity, force, field strength, that remain structurally identical regardless of when you apply them. Wednesday's gravity is Tuesday's gravity. The electromagnetic force that accelerated an electron this morning will accelerate an identical electron this afternoon by exactly the same amount under identical conditions. The laws do not have a timestamp. That absence of a timestamp is the symmetry, and through Noether's theorem, that symmetry is exactly what generates conservation of energy. The mathematics works as follows in plain terms. If the equations governing a system do not change when you shift the time coordinate forward or backward, then there exists a quantity, derivable directly from those equations, that remains constant as the system evolves. That quantity is the energy. It emerges from the time symmetry the way a shadow emerges from an object in light. The symmetry is the cause. The conservation is the consequence. What this means physically is that energy conservation is not a law imposed on top of the other laws of physics. It is a structural byproduct of those laws being consistent across time. Every time the laws hold steady from one moment to the next, energy is conserved as a direct result. The two are not separate requirements that nature happens to satisfy simultaneously. They are one requirement, seen from two different vantage points. This also clarifies something that otherwise seems puzzling. Energy conservation breaks down in the expanding universe. Photons lose energy as space stretches, and there is no global conserved energy quantity in a space-time that is changing over time. That breakdown is not an exception to Noether's theorem. It is a confirmation of it. The expanding universe does not have time translation symmetry. The metric of space-time, the structure that determines distances and durations, is changing as the universe grows. The laws of physics are locally the same, but the background they operate against is evolving. Remove the symmetry, and the conservation law it produced disappears with it. The theorem predicted exactly this. The logic holds all the way down. What remains is a question about the conservation law itself, about what it actually means for the total capacity of an isolated system to stay fixed, while everything inside it is constantly changing form. The number holds, but what exactly is being held? A sealed room contains a burning candle. The wax reduces. The air composition shifts. Light and heat radiate outward from the flame and press against the walls. Every component of the system is changing. The candle is not what it was a minute ago. The air is not what it was. The temperature distribution across the room is not what it was. Change is happening at every scale simultaneously, from the molecular bonds breaking in the wax to the convection currents reorganizing the air above the flame. And yet the number that describes the total capacity of the sealed system does not move. Add up the kinetic energy of every moving particle, the potential energy stored in every remaining chemical bond, the electromagnetic energy carried by the light bouncing between the walls. The sum holds. Not approximately. Exactly. That exactness is what makes conservation a structural feature rather than a statistical tendency. It is not that energy usually stays constant in isolated systems, the way temperature usually equalizes over time or pressure usually distributes evenly. It stays constant the way two sides of an equation stay equal, because the relationship that produces the equality is built into the structure of the laws, not into the behavior of the matter. The candle does not conserve energy because wax has a tendency to be careful. It conserves energy because the laws governing every interaction inside that room are time-symmetric, and time-symmetry makes any other outcome mathematically unavailable. This is also what isolated means in this context, and the word deserves precision. An isolated system is one where no energy is entering or leaving across its boundary, no heat conducted through the walls, no light escaping through gaps, no work being done on the system from outside. In practice, perfect isolation is an idealization. Every real system leaks something, but the idealization is useful because it draws a clean boundary around the accounting. Inside the boundary, the total is fixed. Anything that crosses the boundary changes the total by exactly the amount that crossed. The ledger extends to include whatever the boundary now encloses. This is why the concept scales. A single atom in an isolated potential well, a gas in a sealed container, a planet orbiting a star with no external perturbations. Each is a different scale, a different set of interactions, a different cast of physical processes, and in each case, the total energy of the isolated system remains constant, while the internal distribution shifts continuously. The constancy is not a property of any particular process inside the system. It is a property of the system's boundary and the time symmetry of the laws operating within it. What changes, always and without exception, is the form. The candle's chemical energy becomes thermal energy, becomes radiative energy, becomes the slightly increased thermal energy of the walls. The number that was assigned to one configuration gets reassigned to the next configuration as each interaction runs its course. The total is preserved, not because something physical is being passed carefully from hand to hand, but because every law governing every handoff is operating under the same time-symmetric rules that made conservation unavoidable from the start. The form is endlessly flexible, the total is not, and that endless flexibility of form is the next problem. Because if the same conserved number can describe the motion of a cannonball, the temperature of a gas, the configuration of a chemical bond, and the oscillation of an electromagnetic field, then the concept of a single conserved quantity is doing something remarkable. It is finding common ground between phenomena that look, on the surface, like completely different categories of physical reality. That common ground has a name, and understanding what the name actually points to requires looking at what a form of energy really is. The word form, as in forms of energy, carries a hidden implication that causes trouble. It suggests that kinetic energy and thermal energy and chemical energy are different varieties of the same substance, the way red wine and white wine are different varieties of the same drink. Same underlying stuff, different surface character. But that picture reintroduces exactly the substance intuition that the previous layers have been quietly dismantling. Forms of energy are not varieties of a stuff. They are expressions of the same conserved quantity through different types of physical interaction. The distinction matters because it changes what you are looking at. When a moving object slows down and the surface it's scraped against heats up, nothing was poured from one container into another. What changed was the type of interaction through which the conserved quantity was being expressed. Before the collision, the quantity was showing up as organized bulk motion, all the atoms in the object moving together in the same direction at the same velocity. After the collision, the same quantity was showing up as disorganized atomic motion, the atoms in both surfaces vibrating faster in random directions. The total capacity of the system to produce further change did not shift. The structural channel through which that capacity was expressed changed completely. Each form of energy is defined by the type of interaction it belongs to. Kinetic energy belongs to the mechanics of mass in motion. It is the expression of the conserved quantity through the interaction between mass and velocity. Gravitational potential energy belongs to the interaction between mass and a gravitational field. It is the conserved quantity expressed through positional relationship within that field. Electromagnetic energy belongs to the interaction between charges and fields. It is the conserved quantity propagating through oscillating electric and magnetic configurations. Chemical energy belongs to the interactions between electrons and atomic nuclei. It is the conserved quantity stored in the geometry of molecular bonds. None of these are separate things that happen to convert into each other. They are the same quantity, appearing differently, because the interaction type through which it is expressed has changed. The quantity itself has no preferred form. It takes whatever form the current physical situation makes available. Push a charged particle, and it gains kinetic energy. Let it interact with a field, and that kinetic energy becomes electromagnetic energy. Let the field interact with a molecule, and the electromagnetic energy becomes chemical energy. The particle, the field, and the molecule are different physical entities operating through different interaction types. The conserved quantity moves through all of them without changing its total, because each interaction is governed by time-symmetric laws that make any other outcome unavailable. This is why the number of forms is not fixed by any deep principle. Physicists identify forms of energy based on the interaction types they understand well enough to quantify: mechanical, thermal, chemical, electromagnetic, nuclear, gravitational. These categories reflect the structure of known interactions, not a taxonomy of different substances. As the understanding of interactions deepens, the accounting sharpens. When nuclear physics revealed that mass itself is a form of the conserved quantity, that the rest mass of a particle encodes an enormous capacity expressible through interactions at the nuclear scale, it did not add a new substance to the list. It revealed that a previously unaccounted interaction type had been carrying the quantity all along. The conserved quantity was always one thing. The forms were always just the faces it showed depending on which interaction was doing the expressing. What has not yet been examined is what it means for a form to exist at all, what the physical structure of a channel actually is, and why the same quantity can flow through such radically different physical structures without losing its total. A guitar string vibrates. The disturbance travels through the air as a pressure wave. That wave reaches the membrane of an ear and sets it oscillating. The oscillation triggers electrical signals in the auditory nerve. At each stage, the physical medium is completely different. Tensioned string, compressible air, biological membrane, electrochemical gradient, and yet something threads through all of them continuously. Not a substance passing from one to the next, but a structured pattern of change propagating through whatever physical system is available to carry it. That propagation is what a channel actually is. A structural channel for energy is not a pipe or a wire in the intuitive sense. It is a physical system whose internal degrees of freedom, the ways its parts can move, deform, oscillate, or reconfigure, are capable of sustaining a pattern of change over time. The string can vibrate because it has tension and mass distributed along its length. The air can carry a pressure wave because its molecules have mass and interact through collisions. Each medium has a specific set of ways it can change internally, and those ways determine what kind of pattern can propagate through it, and therefore what form the conserved quantity takes while it is being expressed there. This is why different interaction types produce different forms. The degrees of freedom available to a system of masses moving through space are different from the degrees of freedom available to a system of charges interacting with a field. Kinetic energy expresses the conserved quantity through the translational degrees of freedom of massive objects. Thermal energy expresses it through the vibrational and rotational degrees of freedom of atoms and molecules. Electromagnetic energy expresses it through the oscillatory degrees of freedom of electric and magnetic fields. Each channel has a different internal structure. Each structure supports a different pattern of change, and the conserved quantity takes the form dictated by whichever channel it currently occupies. When energy converts from one form to another, what is happening physically is that the conserved quantity is transitioning between channels. An interaction at the boundary between two systems, a collision, a chemical reaction, an absorption event, couples the degrees of freedom of one channel to the degrees of freedom of another. The pattern of change that was being sustained in the first channel begins to be sustained in the second. The total capacity does not change because the laws governing the coupling are time-symmetric, but the structural home of that capacity shifts from one set of physical degrees of freedom to another. This framing resolves something that otherwise seems puzzling about energy conversion. When a chemical bond breaks and releases what physicists call chemical energy as heat, it can seem as though something hidden inside the bond was liberated, but nothing was hidden. The bond was a configuration of electrons and nuclei held in a particular geometric relationship by electromagnetic interactions. That configuration was a channel. It sustained a pattern of electromagnetic and quantum mechanical change that kept the system in that arrangement. Breaking the bond coupled those degrees of freedom to the thermal degrees of freedom of the surrounding molecules. The capacity that had been expressed through the bond geometry began being expressed through the increased random motion of nearby atoms. Same quantity, different channel, different form. What this means is that the diversity of energy forms is not a fundamental feature of the conserved quantity itself. It is a feature of the diversity of physical systems that can act as channels. The quantity is one. The channels are many. And the reason the quantity can move between such radically different channels without changing its total is the same reason it was conserved in the first place. The laws governing every channel and every transition between channels share the same time translation symmetry that made conservation unavoidable from the start. The symmetry does not care which channel the quantity occupies. It only requires that the total across all channels remains fixed. Point a detector at a moving object and measure its kinetic energy. The detector does not find energy sitting inside the object the way a thermometer finds temperature at a surface. It measures the object's mass and velocity, feeds those values into a formula, and returns a number. The energy was never directly read off the object. It was computed from quantities that were directly measured. Mass and velocity are observable. Energy is what you calculate once you have them. This is not a limitation of current technology. It is not a gap that better instruments will eventually close. It is a consequence of what energy actually is. A quantity assigned to a state cannot be observed directly because states are not objects. You cannot hold a state under a microscope. You can only measure the physical parameters that define the state: position, velocity, temperature, field strength, molecular configuration, and then use the laws of physics to derive the energy value those parameters imply. The measurement always goes through the parameters. The energy is always the output of a calculation, never the input of a direct reading. This becomes sharper when you consider that energy has no absolute value. Only differences in energy are physically meaningful. The kinetic energy of a moving object depends on the reference frame of the observer. Shift to a frame moving alongside the object, and its kinetic energy drops to zero. Gravitational potential energy depends on the reference point chosen for zero height. Internal energy of a system can always have an arbitrary constant added to it without changing any physical prediction. The laws of physics only ever invoke energy differences, the gap between an initial state and a final state, the amount by which one configuration sits higher or lower than another in the landscape of possible states. What this means is that no measurement ever returns the energy of a system. It returns a difference. The calorimeter measuring the heat released by a chemical reaction is measuring the gap between the energy of the reactants and the energy of the products. The voltmeter measuring electrical potential is measuring the energy difference per unit charge between 2 points in a circuit. The spectrometer measuring the frequency of light emitted by an atom is measuring the energy gap between two electronic states. Every instrument, in every context, is measuring a difference between states, and the conserved quantity is the thing that guarantees that difference is consistent and predictable. That guarantee is what makes energy scientifically useful, despite being unobservable in itself. Because if the total is conserved, then every difference is constrained. Knowing the energy of the initial state and the final state tells you exactly what must have happened in between, even if you did not watch it. The unobservable quantity disciplines all the observable differences into a consistent structure. It is the invariant underneath all the measurements, never directly seen, always indirectly confirmed through the relationships between things that can be seen. What this points toward is something quietly radical about the concept itself. Energy is not discovered in matter the way elements are discovered in ore. It is not a hidden constituent that careful enough analysis will eventually isolate. It is inferred, constructed from observable behavior, and shown to be consistent, which raises the final question the chain has been building toward all along. There is a difference between finding something and inferring it. Finding requires the thing to exist independently enough to be isolated and confirmed directly. Inferring requires only that the behavior of other things is consistent with the inferred quantity being real. Energy belongs firmly in the second category. It has never been found. It has only ever been inferred from the behavior of matter and fields, consistently, without exception, across every condition physics has managed to test. What makes that inference secure is not repetition, it is structure. Energy is not a convenient fiction that physicists agreed to use because it simplified calculations. It is a quantity whose conservation is mathematically guaranteed by a symmetry that every known physical law possesses. If the laws are time-symmetric, something with the mathematical properties of energy must be conserved. The behavior of matter could not be otherwise without the laws themselves changing. The inference is as secure as the symmetry that demands it. But secure is not the same as tangible. Energy is not a constituent of matter. It is not woven into the fabric of space. It is not a field existing independently alongside the electromagnetic or gravitational field. It is a description, precise, quantitative, structurally necessary, of what physical systems are capable of doing to each other. It lives, if it lives anywhere, in the relationship between the laws and the states those laws govern. When physics says energy is conserved, it is saying something more specific than it first appears. It is not saying a substance persists through change. It is saying the laws governing change are themselves unchanging across time, and that unchanging character forces a particular quantity to remain fixed as any isolated system evolves. The conservation is a shadow cast by the symmetry. The symmetry is a property of the laws, and the laws are the deepest level at which current physics can answer the question. The warmth of the cup, the motion of the billiard ball, the chemical fire of combustion, these feel like contact with something real and immediate. They are contact with something real. The interactions are real. The changes in configuration are real. The differences between states are measurable. What is not a standalone thing, existing independently of those interactions, is energy itself. It is the pattern those real things conform to, the consistency running through all of them, the number that holds. Pull the whole chain back into a single view: a warm cup, a compressed spring, a burning candle, a billiard ball crossing a table. Each of these looks like a story about things, objects with properties, substances with locations, forces with directions, and at the surface level, that description is perfectly adequate. It gets the engineering done, it predicts the outcomes, it builds the bridges and charges the batteries and lands the spacecraft. But underneath that surface, something quieter is happening. The laws governing every one of those situations share a property that has nothing to do with the specific objects involved. They do not change with time. The rule that determined how the billiard ball behaved at the moment of collision is the same rule that will govern an identical collision 1,000 years from now. That stability is not a physical object. It is a structural feature of the laws themselves. And through Noether's theorem, that feature casts a shadow into every physical system the laws govern. That shadow is energy. This is what energy actually is. Not a substance moving between objects. Not a fluid filling containers and draining out. Not a hidden ingredient inside matter waiting to be released. It is the conserved quantity that time's symmetric laws are mathematically required to produce. It is what you are left with when you ask what all physical interactions have in common, and the answer turns out to be not a thing they contain, but a pattern they all conform to. The reason energy takes so many forms is that the laws govern so many different types of interaction. The reason it is conserved across all those forms is that all those interactions share the same symmetry. The reason it cannot be directly observed is that it is not a thing to be found. It is a relationship to be inferred between the state a system occupies and the laws that determine where it can go next. And the reason a warm cup feels like it contains something real when it heats your hand is that it does. The interaction is real. The change in configuration is real. The difference between the state of the cup before contact and after is measurable and consistent and exactly what the laws predict. Energy is the name physics gave to the consistency itself, to the fact that the rules do not shift, that the accounting always closes, that the universe runs the same laws this second as it ran the last one. It is not a thing the universe is made of. It is the score the laws keep on their own consistency. And the reason why that score never changes is the same reason physics works at all. The rules were the same when you started reading this, as they are now that you have finished. That stability is not nothing. It is almost everything.